Hello there, Mr. Sutton here, bringing you the Algebra 2 4-4 lesson on factoring polynomials. This one is going to be a two-parter if you're doing the honors version of the course. Otherwise, it's going to be done over 3 parts. And specifically in this one, we are going to be learning how to factor polynomials using greatest common factors, grouping, quadratic form, and also some special cubic formulas that you may not have seen before. In addition, we're going to determine whether a binomial is a factor of a polynomial, and we're going to use synthetic division to actually factor some polynomials. So we'll dive in with a couple of examples right away. We see that they're telling us to factor the polynomial completely. This completely part is kind of important. What we mean by factoring completely is that we want the product of unfactorable polynomials. So basically factor it till you can't factor it more. And also we want integer coefficients. So we don't want any like decimal or fractional things going on with our coefficients. And specifically on this one, we have a kind of a unique situation here. You might notice if you look at these two different problems that all 3 of the terms in each one have variables. So if all of your terms have variables, that's a pretty good sign that you can take out a greatest common factor, at least a common factor that has a variable in it. Now once you've done that, you're also going to want to make sure to try to factor the leftovers. And that little rule there is super important. That goes for any of the factoring techniques we use. On most of these problems, you're going to find that after you've taken the first step, there's still more you can do with what's left over. So with that in mind, pause the video and see if you can completely factor example 1. All right, let's see how that went for you. So I always check to see if there's a greatest common factor before I do anything else, because if I take it out in the beginning, it's going to be easier to deal with whatever's left. And if I don't take it out in the beginning, I'm going to have to deal with it later on anyway, or else my answer is not going to be completely factored. So taking a look at these terms, they all have an x, and that's about it. So if I factor an x out of all of this, that leaves me with x squared minus 4x minus 5. And just like I said up here, let's try to factor these leftovers. You won't always be able to, but often you can. So are there 2 things that multiply to negative 5 and add up to negative 4? Well, 1 and 5 works if we have positive 1 and negative 5. So the full factorization of this one then would be x plus 1, and x minus 5. So we have unfactorable product here and all integer coefficients. We're going to move on to example 2 now. So in a moment I'm going to have you pause the video and try this one out. When you do that, keep in mind that all of our shortcuts and other techniques that we used before are still fair game. So any of those perfect square sorts of shortcuts, and also the AC method if you need it. So pause the video and give this one a shot. All right, so just like before, just like always, I'm going to look for common factors before anything else. So looking at the numbers, we have a 2, a 9, and an 18. Unfortunately, there's no numbers I can take out of all of those, but I can take out a q to the 2nd power. That's the lowest exponent, so that's determining what we can take out of everything. So if I take a q squared out of everything, we now have a 2q to the 2nd power plus 9q minus 9. And taking a look at the stuff inside, since I have an a value inside here that's not 1, I'm going to use the AC method. There's no perfect square shortcuts I can take, so AC method it is. So 2 times negative 18 gives me negative 36. And now I'm looking for numbers that multiply to negative 36 and add up to positive 9. So at the very least, I know both numbers have to be opposite signs because they multiply to a negative. So let me go through my checklist here. We've got 1 and 36, that won't work. 2 and 18 doesn't work. Next up, how about 3 and 12? If I have negative 3 and positive 12, that would add up to positive 9. So that's how I'm going to split this up. So I'm going to do negative 3q plus 12q to split up that 9q. And now that I've split that up into 4 terms, just like I always do with AC method, I'm going to use factoring by grouping on these 4 terms. So I have the q squared that I initially took out. I have now, for the first 2 terms inside here, I have a q that I can take out, That leaves me with a 2q and a minus 3. And then for these last two terms, I can take a 3 out of both of those, right? I think I can do better, though. I can do 6. So 6 comes out of that, and then that's 2q minus 3 there. So I've got the q squared. I've got this 2q minus 3 duplicate parentheses that comes out of everything. And I also have this q plus 6. For our next couple of examples, you might notice that these both have 4 terms in them. We just did a problem that involved grouping as kind of part of a larger process, but I mean if your problem is starting with 4 problems, if there were 4 terms to begin with, then grouping is kind of a logical thing to try out. It might not work, but it's worth a shot. So with that in mind, pause the video and see if you can do this first one, example 3. All right, so taking a look here, always checking for common factors in the beginning, noticing that we don't have any that work with all 4 terms. We next try a little bit of grouping. The first 2 terms, we can take a y squared out of both of those. That leaves me with a y minus 5. And for the next 2, those are both divisible by 6. So taking a 6 out of those, we have a y and a minus 5. So this y minus 5 duplicate comes out of everything. And our leftovers, y squared plus 6, go inside my other parentheses. Now I have to always check after I do a little bit of factoring when it says factor completely. I want to make sure that there's nothing else that I can do. Y minus 5, there's nothing else you can do there. It's first power. But how about y squared plus 6? Well, the only way this could be factorable is if this was like a y squared minus some perfect square. Since it's not, we can't really go anywhere with this, and this problem is done. So let's move on to example 4 now. Pause the video and try this one out. All right, so just like before, we're going to use grouping on this. So first 2 terms, we can take out a z squared. That leaves us with a z plus 5, so kind of similar to the last one thus far. And then for these next 2, we got to be careful here. I'm going to take out a negative 4. And if I do that, that leaves me with a positive z, and negative 20 divided by negative 4 is positive 5. That gets me my duplicate parentheses that comes out of everything. And the leftovers now, z squared minus 4 is my other parentheses. Now I have to double check. Z squared minus 4, can I factor that further? Well, I actually can. This is one of those a squared minus b squared situations where I can square root both things and use a plus and minus parentheses. So I've got the z plus 5 I initially started with here, and now I've got a z plus 2 and a z minus 2 for this last piece. So if you're doing this lesson as part of the Algebra 2 non-honors course, the CP course, then this is the end of part 1 for you. You can pause the video and try out some practice problems on grouping in GCF, and then rejoin us next time. If you're doing the honors, then we're going to do a couple more problems before your part 1 ends. Welcome back, those of you rejoining us from the Algebra 2 college prep course. For the honors, well, you never left, so let's keep going. So these 2 examples here, it's kind of hard to put our finger on exactly what is weird and different about these, except that these exponents look kind of high. I mean, we have 4th power here, we have 8th power here, so it turns out that what these are a good example of, and we'll see this as we dive a little deeper into these are both things that are in what we call quadratic form. Quadratic form is something that is essentially in the format of a times x to some power plus b times x to a power that's half as big as the first power, and then plus a constant. Now it's a little bit difficult to see that this is actually what's going on with our example 5 here because there's no middle term, but you could think of there as being like an invisible 0x to the second power in here. So the most common case of quadratic form is when you have something to the 4th power, something to the 2nd power, and a constant. I do want to emphasize, though, that this form kind of holds true even if you have different numbers, as long as the first exponent is twice the second one and you end with a constant. So if you had like a 6, a 3, and a constant, or an 8, a 4, and a constant, and you could keep going, any of those really fall into this category of problems. Now the hallmark of all of these is that you can actually, the reason we're calling them quadratic forms is that you can use quadratic techniques to factor these. The only difference is you're going to factor these like a quadratic using x to the n as your smallest unit instead of x. So whatever you would do, for example, whatever you would do to factor this little expression here with this x to the fourth, x squared in c, you could break this up into parentheses that had an x squared in each one instead of an x. Now keep in mind you still might need to go a little bit further after you do that, but that's the idea with these problems. So with that hint in mind, pause the video and see how far you can get on example 5. All right, let's see how that went. So if I'm thinking of this as kind of like an x squared quadratic situation, what if this were 16x squared minus 81? Well, that would be kind of like an a squared minus b squared situation, and I would square root things and put those in a plus minus parentheses. So if I try that here, I'm going to get 4x to the second power instead of 4x, and then plus 9, and then I'll have 4x squared minus 9. So again, really doing what you would do with x, only using x squared instead of x. Now once we've done this, as always, let's see if we can go a little bit further. We can't do anything with the sum of two perfect squares, or the sum of really anything if there's just two terms, but with the difference we can split that up just like we did with the original. So this 4x squared plus 9 stays the way it is. 4x squared minus 9, though, we can use the square root shortcut again and break this up into 2x plus 3. Those are our square roots now. And then 2x minus 3. And this is fully factored. So we're going to go on to example 6 now. This one does kind of fit into this pattern, I promise, but you may need to do something first before you can see it clearly. Hint, hint, nudge, nudge, pause the video, give it a shot. So like always, we're checking to see if there are any common factors I can take out before I consider any other techniques. So we have a 3, a 15, and an 18. I can definitely take a 3 out of all those, and my lowest exponent is p squared, so I can take that out as well. So 3p squared. That's going to come out of our first term, giving us a p to the 6th power, 8 minus 2. This will now be, for our middle term, we have a 5p to the 3rd. And finally, this is going to be 18p squared divided by 3p squared. That's going to be 6. Looking at the stuff inside here to see if I can go further, I notice that my first exponent is twice my second exponent, and I've got a constant. This is a 2n n constant kind of situation like we have with quadratic form. So I'm going to factor the stuff inside here like a quadratic, only instead of using p, I'm going to use this middle exponent p cubed. So I've got the 3p squared I took out initially, and in here I'm looking for things that multiply to 6 and add up to 5, a very basic kind of factoring here. 1 and 6 doesn't work, but 2 and 3 do if they're both positive. So I can write this as p cubed plus 2 and p cubed plus 3. I do have to keep checking though because I've got things that are higher than first power. Can I break up these cubic terms any more than I already have? It turns out I cannot. But in our next example, we're going to see things that you can do if at least one of these had a perfect cube as the constant. More on that later, but for now we're done with this one. So if you're doing this as part of the Algebra 2 Honors course, this is actually the end of your Part 1. You can pause the video and go do some practice problems that involve these quadratic form sort of situations. If you're doing the CP non-honors course, then you're halfway done with this part of the lesson. We're going to keep going and explore these cubes a little bit more. For these next two examples, it's kind of hard to see with example 8, but on example 7 we have a difference of two perfect cubes. So it turns out when you have two perfect cubes either being subtracted or added, it actually works in either case. Kind of interesting with these cubes. Then there's two shortcut formulas we can use to factor these. So I'm going to show these both to you now. Let's say that we have a cubed minus b cubed, as we do on this first problem. So that can be factored into the following. we're going to take some cube roots, and we can write a minus b as one factor, and the other factor is going to be a little bit bigger. We're going to have a squared plus ab plus b squared. And I'm not going to prove this, but you could very quickly prove it to yourself. If you just multiply these out, we've done multiplying with the 2 by 3 before, you will see that pretty much all the middle terms cancel out, and you're just left with an a cubed from the a times the a squared and a minus b cubed from negative b times b squared that you had in the beginning. All right, so that's one shortcut. Now there is a plus version of this if we have a cubed plus b cubed, and that shortcut, it turns out, is very similar. Instead of a minus b, we're going to have a plus b. We're still going to have a squared, but now we're going to have a minus ab, and we're still going to have a positive b squared. And again, you could prove this to yourself if you want by multiplying this out and seeing that it actually does work. Now, one thing that is important to note here, because a lot of you are going to look at this a squared plus ab plus b squared and be like, hey, wait a sec, I could factor that into a plus b quantity squared. You actually can't. You're thinking of a squared plus 2ab plus b squared. Very similar, but not the same. It turns out the stuff in this second parentheses is completely unfactorable. So just keep that in mind as you're going through here. So with these formulas in mind, pause the video and see if you can apply one of these to help you out with example 7. All right, let's see what happened with this one. So in order to use these formulas, if you have two perfect cubes, you need to, at least mentally, you could write it out if you want, take the cube root of the first and the second term. The cube root of x cubed is just going to be x, and the cube root, the thing I have to cube to get 125, is going to be 5. 5 to the third power is 125. So these are my a and my b that I'm going to plug into one of these formulas. Since I'm subtracting these, I'm going to use the a cubed minus b cubed formula. So I'm going to have the x minus b minus 5. Then I'm going to have a squared, so that's going to be x squared, plus ab means we're doing plus x times 5, so plus 5x. And then plus b squared, we're doing 5 squared, so that's a plus 25. And again, we have to remember that this second parentheses, as factorable as this looks, it actually is not factorable if you think about it. Two things that multiply to 25 and add up to 5, there's no way to do that. So this one is actually done. All right, so we're going to do one more problem that is in some way related to this stuff up here. Pause the video and try out example 8. So hopefully you've been noticing now that there's kind of a trend. We like to throw in these problems where there's a GCF to take out first. In this case, we can definitely take out a 2. Can we do better than 2? I don't think so. 4 would be nice, but we can't take that out of 54. And if 4 doesn't work, then 8 certainly isn't going to work, or 16. So let's take out a 2. And we'll also take out an s squared, since we have an s squared at least in both of these terms. So taking out a 2s squared, that gives us 8s to the third for our first term and 27 for our next term. Now 8s cubed, that is a perfect cube. So is 27. So we actually can use one of these shortcuts. So I've got the 2s squared I took out initially. Now the cube root of 8s cubed, that's going to be 2s. And the cube root of 27 is 3. Since we have a plus between these, we're using this plus version here. So we've got 2s plus 3. Next, I need to do my a squared. 2s squared is 4s squared. Then we have to do minus ab. So that's going to be negative 2s times 3. So negative 6s. And then finally, b squared is 3 squared. So that's a plus 9. And that one's also done. If you're doing this for the CP Algebra 2 non-honors, this is the end of part 2 for you. You can pause the video and have some fun with cubic shortcuts and also those quadratic form ones. If you're doing the honors, then let's keep going. We got lots more in store for your part 2 here. Welcome back if you're rejoining us from Algebra 2 CP, or if you were there the whole time from honors. Let's take a look at something called the factor theorem. So for these two problems down here, they want us to determine whether the binomial x minus 2 or x plus 5 is a factor of the polynomial. And there's lots of reasons we might want to determine this, but what is this really getting at? So the factor theorem is what's going to help us out here. The factor theorem says if p of k equals 0, if I plug some number into this polynomial and I get a result of 0, or, saying the same thing, if I divide a polynomial by a binomial, like f of x by x minus 2, and I get a remainder of 0, we know that these are the same thing, by the way, from the remainder theorem. If either of these two things happens, then that means that this binomial, x minus k, is a factor of the polynomial, f of x. Now, the reason this has to be true is if x minus k is a factor of a polynomial, that means I could actually break the polynomial up into x minus k times some other thing, and then if I plug k into that, k minus k would zero out the entire polynomial. That's kind of a quick, informal proof of what's going on here. So that's the basic idea. If you want to see if something is a factor of something else, either plug in the k value directly or divide with synthetic division, see if you get a remainder of 0. If you get a 0, then yeah, you just found a factor. If you get something other than 0, then nope, no factor here. Pause the video and try one of those approaches with example 9. All right, so there's two ways you could go on this one. One of these would be to do synthetic division. So let's go ahead and try that approach first. So writing out our coefficients, we've got a 1 for the x squared, 2 for x, and then a negative 4. And then our k value, what zeroes out our factor here, is going to be 2, because 2 minus 2 is 0. So drawing our line and bringing down our first coefficient, we've got a 1 down here. And then k value of 2 times the 1 gives me a 2 up here. 2 plus 2 is 4. 2 times 4 is negative 8, or positive 8 rather. And negative 4 plus 8, that's going to give us 4. Since we have a remainder of 4 and not 0, really the key is whether or not it's 0, that means that x minus 2 is not a factor of this polynomial. Now, another way that you could have done that, if you wanted, you could have just plugged 2 directly into the f function. So 2 squared plus 2 times 2, that's 4 plus 4, which is 8, minus 4 would also give you this 4 that we got by using synthetic division. And that'd be another way to see that since we didn't get 0, we don't have a factor. Now, in some situations, it might be actually a lot faster just to plug the thing directly into the polynomial, especially if you have like something to the 99th power and you're just plugging in 1. But one thing that you will lose if you do that is you're not going to have these quotient numbers down here. It might not matter if this thing wasn't a factor anyway, but if this does turn out to be a factor, these quotient numbers could be helpful. So with all of that said, let's move on and try out example 10. Pause the video and give this one a shot. All right, so this one looks like it'd be kind of annoying to plug it in directly, so I'm definitely using synthetic division on this. So we've got a 3, a 15, a negative 1, and I need to be careful here. There's a placeholder 0 for the x that's missing, and then 25. K value is going to be negative 5 based off of the x plus 5. So we bring down our 3. Negative 5 times 3 is negative 15. That plus 15 gives me 0. Negative 5 times 0 is 0. That's kind of nice. Negative 1 plus that is 0. Negative 5 times negative 1 is 5. 0 plus 5 is 5. And negative 5 times 5 is negative 25, which adds up to 0 with the 25 there. So since we got a remainder of 0 this time around, that proves that x plus 5 is a factor of f of x. For this next problem, we're going to do something a little bit different, but still related to figuring out if something's a factor or not. Here they want us to show that this binomial, x plus 2, is a factor of h of x, and then they want us to factor the polynomial completely on the basis of that. So let's let you do the first part first. Pause the video, see if you can figure out whether x plus 2 is or is not a factor of h of x, and then maybe figure out the quotient if you want. All right, well, let's see how that went. So using a little synthetic division, we've got 1 for the first coefficient on x cubed, followed by a minus 1 for the negative x squared, and then negative 24 and negative 36. Our k value that zeroes out our binomial is going to be negative 2. Let's draw our line for our synthetic division. Bringing down my first coefficient, we've got a 1 down here. Negative 2 times 1 is negative 2. Negative 1 and negative 2 gives me negative 3. Negative 2 times negative 3 is 6. Negative 24 plus 6 is negative 18. And then negative 2 times negative 18 is positive 36. Add that to the negative 36, and we've got a 0. Since we have a remainder of 0, this is what proves that we have a factor in x plus 2. So how can we use this to actually factor this polynomial? Well, if x plus 2 is in fact a factor of h of x, that means I can factor h of x into x plus 2 times something else. What is the something else? Well, x minus k in general is a factor. You can do x minus k times whatever your quotient is, because when you divide the polynomial by this factor, you get these leftovers. So that means the divisor, x plus 2 times the leftovers, is your polynomial. So we've got x plus 2, and now our quotient, 1x squared, because it's 1 lower than we started with, minus 3x minus 18. And just like before, we always want to check to see if we can go a little bit further if we have something higher than the first power, like this x squared. So we've got the x plus 2 from the original, and now are there two numbers that multiply to negative 18 and add up to negative 3? So we've got 1 and 18, which doesn't work. 2 and 9 does not work. 3 and 6 works if we have positive 3 and negative 6. So we can factor this into x plus 3 and x minus 6. And now we are factored completely. So here's our last example. This is another one where you need to show that the binomial is a factor and then factor the polynomial completely. Pause the video and see if you can go all the way with this one. Alright, so we can do this exactly like we did the last problem, and I'm going to show you that. But before we do, it is worth looking to see that we actually have 4 terms here. So if all you needed to do was factor this completely, you actually could try factoring by grouping, and you would see that this would get you all the way to a solution. But since you also have to show that x plus 3 is a factor, we might as well do the synthetic division route. So let's set up our synthetic division. We have a 1 for the x to the 4th, 3 for the 3x cubed, and notice we're missing an x squared here, so we need a 0 for that placeholder, followed by a negative 1 for the negative x, and negative 3. Since x plus 3 is our factor, we use negative 3 for the k value over here. Let me do my synthetic division line and bring down my first coefficient of 1. Negative 3 times 1 is negative 3. That gives us 0 here. Negative 3 times 0 is 0, plus 0 is 0, times negative 3 is still 0, plus negative 1 is negative 1, times negative 3 is positive 3, and then as expected, when we add these together, we get the 0 at the end. If we didn't, then we'd kind of be in trouble. So because we have a remainder of 0, again, this proves that whatever you're looking at, x plus 3 in this case, is a factor. So that means we can factor this into x plus 3 times our quotient here. Now the quotient, since we started with x to the 4th, this 1 represents 1x to the 3rd power. We have a 0 for the x squared, which we're not going to write. We have a 0x that we don't need to write. And then we have a minus 1 completing this quotient. Can we factor x cubed minus 1 further? Well, this is a difference of cubes. We have a shortcut formula for that we learned earlier on in this lesson. That was this one right here, a minus b, a squared plus ab plus b squared. So let's bring down the x plus 3 that we already had, and now breaking up this x cubed minus 1, cube root of x cubed gives us the a value of 1 for that first parentheses. Cube root of 1 is also 1. So we've got, let's see, x minus 1. And then we've got a squared is going to be x squared, plus ab is just plus x times 1, so plus x. And then b squared is just 1 squared, so just plus 1. And that's as far as we can get on this one. So that is it for this journey. Hopefully this lesson was the key factor in helping you make sense of polynomials. Till next time, Mr. Sutton signing off.